Hi, my name is Vincent. I am a professor at Carnegie Mellon University, where I study how AI can help software developers. I chose this direction because I firmly believe that AI can help make programming easier, safer, and more accessible. I am also a programmer, and as such I've always been passionate about the transformative power of open source code. In the past few years, something amazing has happened. These two interests have started to overlap. With the arrival of tools like Copilot, AI is both learning from and serving open source developers. So it's perhaps no surprise that I spend part of my time as a visiting researcher at GitHub, working to improve AI solutions for programmers by trying to better understand the needs of open source developers. Based on this experience, here's my pitch. AI for code needs open source. I don't mean for data. I mean that open source is a key part of the future of AI. I actually think this is true for all of AI, but I will focus on code in this talk because that is the domain I know best. If you spend time on the AI side of GitHub, you've probably already noticed this. When new models are proposed in the research community, developers on GitHub quickly provide implementations and come up with improvements. For example, if you search for a cutting-edge machine learning model, I can almost guarantee that a nice implementation by @LucidReigns will come up. There are now more than 1 million GitHub repositories related to AI, and this number is climbing fast. So far this year, more than 1,000 such repositories have come alive every day. This helps me as a researcher. I often prefer to read and run the code over equations in a paper, and it helps the community to create new variations of proposed models. Models themselves are also more and more often released on platforms like Hugging Face. Developers are integrating these into new, smart tools and calibrating them for new scenarios. So the open source community is accelerating the improvements in AI and is making AI more broadly accessible and useful. I will share some examples in this talk. Specifically, I'm going to do 3 things. First, I'm going to do a bit of teaching, I'm sorry, but I cannot help it, and explain the very basics of what happens behind the scenes in tools like Copilot that generate code for you. I will tell you about what language models are and what has changed in the last few years that makes them so powerful now. Second, I will give several examples of how the open source community has responded to these exciting changes. I will talk about how these tools evolved and how well they perform on metrics that try to capture what developers need. And finally, I will talk about the open challenges that remain, not just to make better models, but to build tools that are more accessible and useful to developers. When explaining how AI for code works, I always like to start with a code snippet. Any developer looking at this will recognize that we're about to start writing a for loop. That is, we're about to iterate over something. We can tell because we've probably read and written many lines of code with this keyword. So when we see the font and the blinking cursor, we know what's up. We don't quite know what comes next. If you are a Java or a C developer, you probably expect an open parenthesis since that is the syntax used there. I write more Python than anything else these days, so my first response is to expect something like this. Now maybe focusing on Python will have lost me half the audience, but that is actually part of the challenge. If you want to build a tool that supports programmers, it has to work for people doing very different things. There are hundreds of programming languages that are actively used on GitHub right now. If I read on and see these next few tokens, I am pretty confident that we are looking at Python code, and I might think further ahead. I have more context now. I know that we're in a for loop, and the loop variable is called I, so odds are that we're looping over a range of integers. I'd expect the next token to be range, and maybe the ones after that to specify a number. This is what language models do. In a typical language model, the goal is to generate text or code from its context. Let's see that in action. In the previous example, we first saw for, and based on that we might have predicted I to follow. Once we confirm that that is the next token, we can then extend our context with it and query the model again to predict another token. In Python, there will always be in, so that's easy. We repeat this process expanding our code until we've hit some stopping point, like the end of a line. Now obviously, the second token won't always be I. Code is creative, like other languages, so the model can be wrong or it can generate a correct implementation that is different in style from what a developer needs. We train these models by encouraging them to write code that is more like what we might find in public code on websites like GitHub. Now in practice, the model isn't a simple black box. It's a complex neural network called a transformer that contains many parameters. What has changed since the ancient days of 2020 is that this many has started being measured in the billions instead of millions, and so has the number of lines of code that these models are trained on. That might not seem like a big shift, but trust me when I say it is. These many billion parameter, or as we commonly call them, large language models, are much more expensive to train, but they are also far better at predicting source code. Let's zoom in a bit on one of these models here called Codex. Codex was the first large language model of code. It is also the model powering GitHub's Copilot. It derives most of its strength from training a fairly simple but very large model on a lot of code. The result is a model that can quite regularly write entire methods for you, given a reasonable prompt, just based on the millions of patterns it has seen. One of the things this work proved is that training large models is pretty much a requirement for coming anywhere near the capabilities of programmers. Programming is objectively hard, and small models just don't do well at generating correct code for difficult tasks. That's bad news in a way, since these large models are both really expensive to train and quite expensive to query. It takes a lot of dedicated hardware to make this happen. But going back to this chart, you'll notice there are quite a few other large language models, many of them in orange, which means they are publicly available right now. In fact, several more open source models have come out since this chart was made. Most of these models were trained after the release of Codex, in part to better understand the challenge of training such large models for code, and in part to meet the needs of the open source community for freely accessible models. Let's take a look at 3 of these. The first model was Parrot. This was a 1.5 billion parameter language model trained on 50 gigabytes of Python code from GitHub that is available right now on Hugging Face. It comes with a helpful blog post on what it takes to collect this data and train such a model, and it has released all its training data in case you want to train your own. When Parrot came out, it inspired me and several collaborators at CMU to train a separate model that we nicknamed Polycoder. The main reason we did that was to support other programming languages besides Python. So correspondingly, we trained a somewhat larger model to make sure it had the capacity to learn patterns that span across many programming languages. Our model supports 12 languages in one and is quite strong on some of these. For a while, it was even slightly better at predicting C code than Codex, though of course the latter has evolved since then. A few months later, a series of models called CodeGen came out and knocked us off the largest open source model of code throne, with models going up to 16 billion parameters. These include both models with multilingual and with Python-only support. A neat related project is Pilot, built by a professor at NYU. Pilot sets up a server around the CodeGen models that lets you host a neural code completion service on your own hardware. You can actually point Pilot to this service and it will serve up completions from your own models using the same plugin. One thing that this highlights is that Copilot isn't a model, it's a tool, just one that talks to Codex by default. It also helps us understand some of the challenges for imitating this with open source models of code. Let me explain that by means of a graph. In this plot, I'm going to compare the performance of a whole bunch of models. On the x-axis, I will show the performance of each model expressed in terms of how good it is at implementing an algorithm from a detailed specification. Think of the algorithms as typical lead code problems. This reflects the model's ability to write challenging programs. On the y-axis, I will show performance on writing entire functions from random, well-tested projects on GitHub. The engineers here at GitHub Next built this amazing harness that allows us to find such functions, ask the model to predict how the function should be implemented based just on its documentation and context, and then run the project's test suite on the suggested completions to check if they are correct. A function that passes the test is probably a correct re-implementation of the original. So what this performance reflects is how likely is the model to be able to implement an entire function in a real project correctly in one go. I ran the models on functions from about 100 random Python projects, so let's look at the results. The first 2 models I talked about were Parrot and Polycoder. Parrot is the smaller of the 2 and was the very first open source model, so it makes sense that it doesn't quite do as well. Polycoder is a bit better at algorithmic tasks, but especially performs a good deal better on real functions, solving about 1 in 5 problems in a single guess. Now you might have noticed that the 2 circles are a different size. I'm using size to indicate how fast each model is in terms of how many tokens it can generate per second. Smaller models are faster to query, which matters for some applications. I'm also using a different outline for Polycoder to highlight that it is multilingual. Next came the various CodeGen models. These actually come in 4 sizes, and you can see the progression from left to right as the models get bigger and better. The final model can predict over 30% of real-world functions correctly in one guess. One big advantage that these models have over the previous models that makes them better is that they were trained for much, much longer. They are also all monolingual. For comparison, the multilingual version of the largest model is quite a bit weaker, scoring somewhere around a monolingual model about 1/8 its size. An important thing to notice is that throughput goes way down when models get this big. Again, looking at the size of the circles, the largest model takes quite a while to generate longer functions, even on high-end hardware. It also comes with a significant memory footprint, so most laptops and desktops can't realistically run this model. For this reason, many developers may prefer to use a smaller, faster model. All that said, Codex is quite a bit ahead. It solves about half of each type of challenge function in a single guess. It's also multilingual, and it is really fast to query because it is hosted in the cloud, where it can take advantage of much more powerful resources. And that makes sense. Codex was the first model to come out, and as a commercial product, it has different constraints from open source solutions. Open source models need to be lightweight and fast to query, which naturally comes with a performance penalty. Open source models also have their advantages. If you have the resources, many of these models can be calibrated on your own code in a process called fine-tuning. Although I haven't seen many people do this, it can really boost the model's quality on your future programs to get familiar with your programming style and environment. So for the time being, the story to me is this. Open source models have gotten quite a bit better in a very short period, but they do operate in a different performance domain from Copilot. The optimist in me says, hey, that means there's clearly quite a bit of room for improvement ahead. So let's talk about what is ahead, both how we might navigate the challenges facing current open source solutions and what I think are promising opportunities in this space. Based on these results, I just presented 3 targets seem worth pursuing to make open source models more powerful and accessible to regular developers. 1. To work in a typical software development environment, open source models need to be light and fast. There's quite a bit of unexplored territory here, including model quantization, that has shown really promising results in other fields. I'm very optimistic about this. Looking at image generation, another AI for creativity domain, the open source community was incredibly quick to create and accelerate open source diffusion-based image generators after DALL-E 2 came out. I wouldn't be surprised if models of code can also become 2 to 4 times as small and fast as they are today without performance loss in the next year. 2. Developers rarely write in a single programming language, so models that support multiple languages are going to be more useful. However, as we saw previously, this decreases model performance compared to a model trained for one language only. One solution is to build a catalog of small, language-specific models for a range of programming languages, perhaps all built in the same shared base model. This would lend itself really well to the kind of distributed setup at which the open source community excels. And finally, there's always room for improvement, and we clearly aren't close to perfection yet. Fortunately, improving model quality isn't just a topic for academic research anymore. These days, I get as many of my insights and ideas from open source projects on GitHub as anywhere else. If you want to contribute, there are several concerted efforts, such as Big Science's Big Code project, which aims to train a 15 billion parameter model of code by bringing together many experts working on different components in parallel. Overall, I am excited for the future. Models like the ones that have emerged in the last 2 years have the potential to save developers many hours of tediously writing code, which frees us all up to focus on the more creative, big-picture aspects of software engineering. My long-term hope is that these tools will make programming itself more broadly accessible. With models taking care of the coding, many people who are non-programmers today could instruct a computer to do simple things in a familiar, natural language tomorrow.